Hello, welcome to Project 152, your weekly specialist exam prep. Now, this week is a super exciting week because it is week 30, the final week of this. Now, if you'll have done every single one of the 30 weeks, you'll have done all 152 questions that the QCAA has ever done. All right, let's get stuck into it. So question 1 here, and we're looking at confidence intervals. Now this is an interesting one because it says based on this sample and using a Z value of 1.5. So it's a tech active question that feels like maybe you could just put it into the confidence interval calculator of your calculator, but instead we're going to have to use this formula right here, and where it says Z, we're going to sub the value 1.5, and all of the other stuff is going to get subbed in as well. So nice big equation here. X is our mean, and it says our sample mean is $1.52, and then we're going to subtract Z, which is 1.5, multiplied by fraction. Now our standard deviation is 0.14, and then root, the sample size is 50 petrol stations. Now that's going to be our lower limit, and then I'll just write the whole thing out again with plus instead of minus for the upper limit. Alright, so that's it, same thing, just with a plus in it. And when I type this into my calculator, I get 1.49 and I get 1.549, I think, which obviously we can round here to 1.55. Get rid of that 9. Alright, so our final answer, we can see it in the multiple choice there, it is 1.49. 1.55. Fairly straightforward, plugging things into your calculator. It's unique because it's the only time I've seen this like Z value of 1.5 rather than a confidence interval of 95% or 90% or some other percent. All right, celebrate. Next question. More confidence intervals here, and this one's an interesting one because it's using your knowledge of confidence intervals. So here we have a random variable, blah, blah, blah. The confidence interval for a 95% confidence interval is this, 209.7 to 221.9. I'm going to write that down. So I've written it in a pretty non-standard way because I want to demonstrate something. So the confidence interval is from 209 to 221.9. And it says, an approximate confidence interval from you based on the same sample using a confidence level greater than. Confidence level greater than 95%. So we don't know what it is, but it's a larger confidence interval. Okay, to be more confident that mu is within your sample has to grow. Your sample has to be larger. Sorry, not your sample. Your interval needs to be larger. Say like this. But it will still be centered around the same mean. All right, so of these 4 options, we need something that's larger than 209.7 to 221.9. Now, it can't be 210 to 221 because that's smaller. It can't be 215.8 to 228 because that's smaller again. So it must be A or B. All right, and so the question is, A or B, we need to check that they're both centered the same. Now, what's that value there? Well, it's going to be the average of these two, right? Because it's the midpoint. It's the midpoint of these. So I'm just going to add those two values and divide by 2. So when I do that, I get 215.8. So that means that the mean is 215.8, 215.8. All right, so far so good. Now the question is, between A and B, are both of those 215.8? So if I find the midpoint between 206.5 and 223.3, will I get 215.8? Well, this is option A, and I didn't get 215.8. I got 214.9, which means that A is probably wrong, or is wrong. What about option B? Let's test that. All right. Option B, I get 215.8, so it's fulfilled the 2 criteria I needed for an approximate confidence interval based on the same sample with a higher confidence level. Both, it is larger, wider than the original, and it is centered on here. You need to have both of those things. I have a feeling option C or option D, one of them, or maybe both of them, are going to be centered on 215.8, but only option B is also wider. So my answer is B. Celebrate that one and on to the next one. All right, so a very fast question here. I find it easy to read these questions from the bottom up, so I know exactly what I'm doing. Determine the standard deviation of the distribution of the sample mean scores. Okay, straight away, I know I've got a formula for determining the standard deviation of sample mean scores, and it looks like that. Okay, so the question now is, if I'm finding this standard deviation, all I need is the standard deviation of the population. So just look here for the standard deviation of the population. The standard deviation for the scores of 1,000 students completing an entry test at a certain university is 13. Okay, and now I need to look for the sample size because I need that root n. Okay, it'll be tempting here to think the standard deviation of the scores of 1,000 students is the sample size, but 1,000 students is the population. The researcher takes repeated random samples of the test results, with each sample comprising 40 scores. The samples each have 40 scores, so the sample size is 40. Type that into your calculator and we are done. I get an answer of 2.055. Now I don't see 2.055 in my solutions, but I do see 2.06, and that's my answer. Very straightforward, very nice. They do put some little like sneaky bits to try to trick you up. One of those solutions will have you putting 1,000 in for n instead of 40. Something to watch out for. But otherwise, that's a nice one. Celebrate. Next question. So a nice little question here with a part A, part B, and part C. So we're just going to do each of those in turn. So let's just focus on part A for now. Determine the probability that whatever this is less than 25. Now what's that? Travel times are collected from a random sample of 120 of these students and used to calculate a sample mean. Okay, and that's a sample mean. So part A says, determine the probability that the sample mean is less than 25. All right, so if we're calculating the probability that a sample mean is less than or greater than or whatever it might be, we're dealing with the normal distribution, because those sample means will be normally distributed, particularly because we can see we're taking large sample sizes of 120. All right, now the mean of this is going to be equal to the mean of the population, so let's find that. The travel time for students attending a certain with a population mean of 25.2. Okay. Now, what else do we have here? Okay, and we have a standard deviation of 4.7 minutes. Now, that is not going to be the standard deviation, 4.7, because 4.7 is the standard deviation of the population, but we want the standard deviations of the sample means, and we've got a formula for that. Here we go. Okay, so to find that standard deviation, feels like deja vu because I did in the last question. We're looking for the population standard deviation, which is 4.7, and dividing it by the square root of the sample size, random sample of 120. All right, and I might just keep that number like that because I'll be able to use that number in my calculator for my standard deviation. I think that's all I need to do. Now, what it says is determine the probability that the sample mean is less than or equal to 25. So that's where 25 is, and we're finding this probability right here. Calculator time. So we're going into statistics. Let's jump into there, and we're going into distributions, normal distributions, and we're finding the probability under a normal distribution. All right, now the lower, we can just make an extraordinarily lower value, all right, because we're trying to take in everything here. Now the upper value is 25. Now the standard deviation is going to be this, 4.7 divided by the square root of 120. Okay, and then the mean is going to be here, 25.2. All right, I like to scroll down, make sure I draw it. All right, looks exactly like the sort of thing I'm looking for. My answer here is that the probability that the sample mean is less than or equal to 25 is exactly that. We can switch it to a percentage if we want, 32.055%. that's the answer to part A. Draw a nice little picture, show that you know what the standard deviation is, and then calculate it. So part B, we can see, is like a 1-mark question. So we just got to find the answer. Given the probability that the sample mean is greater than k is equal to 0.9, determine the value of k. All right, you want to be good at drawing this picture. We've got a normal distribution, the same normal distribution that I've got right there, with the same mean and the same standard deviation. But this time we're saying that there's some value k, and the probability of it being, the sample mean being larger than k is 0.9. Larger than, right? And so you might struggle with this a little bit because you might be thinking, well, where am I supposed to put k? Am I supposed to put it here? Am I supposed to put it here? The reason I'm putting k on this side is because it says two things. It says larger than k, so I have to shade to that side of k. But the reason I know I'm putting it on this side and not that side is because the probability is 0.9. It's more than 0.5, so it has to be more than half of the normal distribution I'm shading in. After this, I'm jumping straight into my calculator again. So still in stat mode, we're going to distributions again, normal distributions, and this time we're looking at an inverse normal. This is really method stuff. We're going to do a tail that is a right tail. We're looking for an area of 0.9, a standard deviation of whatever that is. I have a feeling whatever was just in there is the thing I'm looking for. Root 120. Yep. And then 25.2, that's my mean. I'm going to calculate that. Doesn't draw it, unfortunately, which is a bit of a shame. But we get an answer of 24.65. K is equal to 24.65. It's obviously worth checking to make sure that you feel comfortable with 24.65 being a reasonable answer. It needed to be less than 25.2, yes. It needed to be like a little bit, like quite a bit less than 25.2 in the broad scheme of things, because almost everything is included here, right? The standard deviation, our calculator said it's about 0.4 something. So if it's 90%, we'd expect about 2 standard deviations to be like away from it. So it's coming out with about right. So happy with K being equal to 24.65. That brings us to part C, and I might just get rid of all of this stuff unless it's useful, but I don't think it is. Move on to part C. Okay, part C, travel times are collected from a second random sample of the university students and used to calculate a second sample mean in minutes. All right, given the probability of this new sample mean being less than 25 is 0.4, determine the number of students in the second sample. So, an unknown sample size is what we're dealing with. But what do we have? Well, we know that sample means are normally distributed. We know that a sample means mean is equal to the population mean, which is still 25.2. And we know that the probability that this second sample being less than 25 is equal to 0.4. So let's draw that in. Just make a bit of space for myself. This is 25, and the probability that something is less than 25 is 0.4. Now the big problem is I don't know the standard deviation. I don't know the standard deviation because I don't know the sample size, and we know that the standard deviation is equal to the population standard deviation divided by the sample size. Now I do know the population standard deviation. It's 4.7, but that still doesn't really help me. What will help me is a standard normal distribution. Now you should know that a standard normal distribution has a mean of 0 and a standard deviation of 1. And what I'm going to do is do this same calculation, 0.4, and find out what that z-score is. Find out what that z-score is using a standard normal distribution and the inverse normal distribution on my calculator. Now I'm already in inverse normal, but I do need to change some things because I need to change it to a left tail, an area of 0.4. Now the standard deviation is a standard normal distribution, standard deviation 1 and a mean of 0, and I calculate that, which gives me a z-score of negative 0.2533. So now that I know, let's get rid of our calculator for a second. Now that I know that z equals negative 0.2533, I can use my old z-score trick that you should be used to from methods to figure out what this sample size is. All right, let's get started with our z-score. So we know a formula for z-score. We can say that z is equal to the score minus the mean over the standard deviation. Now, the score we've got in mind is 25. The mean is 25.2. The z-score, we know, is negative 0.2533. And we can now solve for that standard deviation. And that's super simple to solve. I think you can solve that without me. So rearranging, solving that for standard deviation, you can just put it into your calculator if you want and ask it to solve it. We get a standard deviation of 0.7896. All right, now our standard deviation is equal to 4.7 over root n. So we've got a nice new formula which says that the standard deviation, which we now know is 0.7896, is equal to 4.7 divided by root n. Now, in this case, I'm not even going to rearrange it. I am just going to type that into my calculator and ask my calculator to solve for n. So I did a solve n on my calculator here, and I get an answer of 35.43 for n. Now, of course, you really can't stop here because it says, given this is true, determine the number of students in the second sample. You can't say that there's 35.43 students in the second sample. So you have to round this. Therefore, n equals 35 students. Nothing else makes sense there. All right, that is part A, B, and C. A fun little question. Part C gets into some weird territory, but it's an interesting question because it could come up in methods as well, just without the SDN, but everything else, like it could easily be a methods question. All right, celebrate. All right, so let's jump in and start reading this question. An object with a mass of 2 kilograms is released from rest at the top of a 1 meter long frictionless plane inclined at 30 degrees to the horizontal. If you're not drawing a picture here, you're mad. I don't have to read the rest of the question before I start drawing a picture. All right, so that's what we've got, 30 degrees, 1 meter long, it's sitting at the top. It says a force of P newtons acting parallel to the plane opposes the motion of the object. All right, so there's some kind of force parallel to the plane, not parallel to the ground, parallel to the plane that's trying to stop the thing from falling down. Friction, probably. All right, when the object is x meters from the top of the plane, its velocity is v. All right. Given the magnitude of P, which is the opposing force, is equal to 4 over root 4 minus x squared. All right, so what we have is a variable force. And this force here is 4 over root 4 minus x squared. Okay, determine x, the distance from the top, when the velocity is equal to 2. Okay, so it feels like we need to be modeling the path of this thing down the plane, using this somehow and using what we know about inclined planes, etc. Now, the thing that I do know about inclined planes is that a good way to start is by realizing that there is a force acting directly downwards, and that force is 2g. Also realizing that it's a good idea to set your I and your j components here parallel and perpendicular to that plane. That means that I can now take this 2g and break it up into j, if I try to make everything parallel, all right, and I components. Okay, and having done plane stuff a lot, straight away I know what the magnitude of this vector is. It's 2g sine 30 degrees. And I know that straight away. How do I know that straight away? Well, this angle here is 30 degrees. This angle here is 60 degrees because those two add up to 90. If that's 60 and this thing I've created is 90 degrees, then that means that this is 30 degrees. If you're following, that's 30 degrees right there. And then it's basic trigonometry to find the opposite side, right? Because we know that sine theta equals opposite, and that's this length here, over hypotenuse. And we know that the hypotenuse is 2g. So we can move that hypotenuse to here, 2g, hypotenuse 2g, and sine theta, not theta, 30 degrees. So this opposite side is 2g sine 30. But this should, because you've done a few inclined planes in the past, you should be able to jump straight from knowing that this is 2g. If this is 2g, this is 2g sine theta, and this is theta. Okay, so 2g sine theta, there is that force acting down the plane, 2g sine 30. And that is the only force acting down the plane. And the only force acting up the plane is this opposing force, 4 over root 4 minus x squared. So we can say that the net force down the plane is equal to, and we need to be a little bit careful here, so 2g sine 30 minus this. So 2g sine 30 minus 4 over root 4 minus x squared. All right, beautiful, nice. We can probably tidy this up a little bit. Sine 30 is equal to 1/2. So 2g times 1/2 is just g. So I get this nice net force is equal to g minus 4 over root 4 minus x squared. All right, so that's force. Now, thinking. I'm talking about velocity. I'm talking about displacement. I've got this nice equation for the force acting down the plane, g minus 4 over 4 minus x squared. I also know that force is equal to mass times acceleration. Great idea to bring mass and acceleration into this because that's going to get me closer to being able to get to displacement and velocity. So, the net force is equal to mass times acceleration, and luckily we know the mass of the object is 2. So we can substitute 2 for the mass. So 2 times the acceleration is equal to g minus 4 over root blah blah blah. So I can divide both sides by 2 now to just say that the acceleration is equal to g over 2. Let's stop talking about g. Let's say 4.9, 9.8 divided by 2. And then 4 over root 4 minus x squared. 4 over root 4 minus x squared. If I divide that by 2, it just means I'm putting another little 2 on the bottom. And so 4 divided by 2, I end up with a 2 on the top. 2 over root 4 minus x squared. That is amazing. Because now, this is the acceleration down the plane. Now, of course, we have acceleration as a function of displacement. And if we look at the question, we're interested in displacement and we're interested in velocity. So we really want to get to some kind of equation where it's velocity and displacement. So luckily we have these neat little formulas here. And if we express acceleration not as acceleration, but instead as v dv dx, we're going to be able to start working with this so that we can get it to that equation, v in terms of x. So now that we've got acceleration, instead we've got v dv dx. So now we just need to start working through this, getting it down to an equation that is v in terms of x. The way that I'm going to do that is to integrate like a separation of variables. So we're going to go the integral of v dv is equal to the integral 4.9 2 over root 4 minus x squared with respect to x. All right, so now we're going to integrate both sides. The integral of v is v squared over 2. Very, very straightforward. Now we've got two integrals to deal with here. The integral of 4.9 is 4.9, and we're integrating with respect to x here. So it's 4.9x. And then this thing here, that's ringing some alarm bells. I'm thinking formula sheet. So a quick look at our formula sheet brings me to this, and we've got sort of three options here that it's reminding me of. Now it's got a square root, so it's like sine or cos, and we can really use sine or cos here. There's no reason to use one over the other, but I'm going to use sine. So everything's pretty much in order here. The only difference is I have a minus 2 instead of a positive 1, but that's fine because I can just put the minus 2 out the front. So minus 2, and then what I'm now integrating is 1 over root 4 minus x squared. And I'm just multiplying it by negative 2 at the end. All right, so this here fits our formula very, very neatly. We've got a 1 on the top, we've got a square root 4, so our a value is 2, and we've got our negative x squared like we expect. And so that means the integral of that is inverse sine x over 2. All right, and of course we've got some plus c hiding in here somewhere. We don't have to put a plus c on both sides. 1 plus c will do it. All right, and so now the question is, how do we find our plus c? Because we're very, very close to having a nice little equation that has v and x in it. We just need to get that c. So we need some sort of conditions that we know. We know that an object with a mass is released from rest at the top of a 1 meter long frictionless plane. All right, so it starts right here, and when it's let go, at the very beginning of being let go, it was at rest, so it had velocity 0. So when it was standing up the top, now, there was something that defined x here. When the object is x meters from the top of the plane. So x represents the distance from the top of the plane. So at the beginning of this whole scenario, the displacement was 0. So all of that is to say that when x equals 0, velocity was also equal to 0. And we can sub these two values into this equation. Now, I've put it all in there, 0, 0, 0 for velocities and x's. You can type this into your calculator, but that is equal to 0, that is equal to 0, and all of this is equal to 0. So therefore, c is equal to 0. All right, so that felt like a bit of a wild goose chase. We put c in there, we did that, but it turns out c is equal to 0, so we never needed c in the first place. This question's really finished now because it says, given this, determine x when v equals 2. So I'm just going to let v equal 2 and solve for x. Now, of course, don't be silly. Don't try to do that by hand. Grab your calculator, solve it that way. All right, so running out a bit of space here, but we'll do it. We've got options, calc, and we're doing a solve, and then we just type in our equation. No tricks there. My calculator gives me an answer of 0.5143. So, recapping, what does all this mean? The object started up here, it started coming down at about the halfway mark when there was 0.5143 meters between here and here. So about here, it had a velocity of 2 meters per second. Great, makes sense, sure, why not? Let's celebrate. Next one. So a very intimidating looking question here. It's question 19. Let's just rearrange things so it's a little bit easier to see what's going on. Now, before we get started, remember, complex unfamiliar questions, you're not expected to be able to do it in a straight line, right? For purposes of this video, I'm going to be stepping through it step by step by step by step. But in the real world, you're sitting down, you're looking at the question, and you're trying to figure out something that you can do, anything, and then you just start from there. So what do I have? The waiting time until workers at a certain call center receive their nth call is a random variable t with this probability density function. Okay, I know things about probability density functions. And we know k is a positive constant. So we know k is some kind of number, but we don't know what it is. The waiting time until workers receive their fifth call is collected from a random sample of 80 workers. All right, so we're thinking samples now. Okay, determine the probability that the mean waiting time from this sample, okay, so sample mean, is more than 16 minutes. All right, so this is when I read this question, what I'm seeing is the exam writer is squashing two ideas together. Probability density functions and then sample means. So I can see that this is a probability density function, and I know that k is a positive constant. So thinking about everything that I know about probability density functions, I think I can solve this for k if I put the right stuff in. All right, so what do I know? Well, I'm interested particularly in the waiting time until workers receive their fifth call. So let's put that 5 in for n into this probability density function and see what it looks like after that. All right, so it's a probability density function. Now, I'm doing it between 0 and infinity because I know that t is greater than or equal to 0. So hypothetically, t can go on forever. And n is equal to 5. And then the next bit says t to the power of n minus 1, so n minus 1 is 4. And then the denominator says n minus 1 factorial, so that's 5 minus 1, which is 4 factorial. Might just turn that into a number in a second. And then we've got e to the power of negative t on 3 with respect to t. Now, the reason I'm integrating this between 0 and infinity, because I know something about probability density functions. The area under the curve for a probability density function must be equal to 1. So I have this fantastic thing going on here, right? This relationship here, and I should now be able to solve this for k. Now, before I start solving this for k, I might just make it easier on my calculator. I don't know if this helps, but I'm going to make 4 factorial equal to 4 times 3 times 2 times 1, which is 24. Okay, and now I'm going to ask my graphics calculator to solve this for me. And there's a real trick to this, so if you think you know how to do it, fine, but there's a good chance you don't know how to do this, so check it out. All right, so we should all know how to solve on our calculator by now. Calc, solve. All right, that's the easy part. Now, just exit out of that and go to math, because now I want to put an integral in here. And I'm going to be integrating between 0 and a large number. Not too large though, because if I put a massive number in here, my calculator is not going to handle it. So think about what this value is. It's time in minutes. We've got waiting times of more than 16 minutes. So I'm just going to put like a smallish number in here, 60. I might try again with a larger number in a second. Okay, and now I need to enter my integral, and that's going to be not straightforward. Need to get to it. Okay, there we go. So it's going to be alpha, the letter K. The reason I'm putting the letter K in here is because I need to put X somewhere else. I need to put X where the T is, right? This is confusing. So X is going where the T is because we're integrating with, our calculator integrates with respect to X. Now, all of that's going to be a fraction, so I wish I'd pressed the fraction button to begin with. That's okay. So we're going to put 24 there, and then we're going to multiply that by Shift E, and we're doing e to the negative x on 3. So now that I've put in that whole thing, remember we're solving it equal to 1. Now you can't just press enter here because your calculator always defaults to thinking that you're trying to solve for x, but you're not trying to solve for x, you're trying to solve for k. So you need to find your comma here, and then you need to click Shift K. So it's like solve this equation, comma, for this unknown, Now it's going to think for a little while. It's going to take a long while, so I'm not going to make you watch that. So it took about 15 seconds, so don't panic if it's taking a long time. I'll click exit out of that, and I get an answer of 0.333333, which is about 1/3. So our answer is k is equal to 1/3. Now, I did just pause it and attempt it with a much larger number, 240. It took ages, took like 45 seconds, but then it did spit out exactly 1/3. So maybe a good idea would be to start with a smaller number like 60 and then attempt a slightly larger number and see how it looks. But either way, that 0.33333 or exactly 1/3, you could proceed with either of those values and you're not going to get it wrong. Okay, so now I've gone one step closer because I now know this probability density function has a k value of 1/3. It's kind of complete now. So I can write it down in its entirety for the wait time for their fifth call, which is what this question's all about. All right, so this is the probability density function. So I've just put in 1/3 for k, and I've also put in 24 instead of 4 factorial. But this is our probability density function for the population of all workers in this call center and the time it takes them to receive their fifth call. All right, so this is the population of wait times for the fifth call. Now, if we're dealing with sample means, we know that we want two things. We want the population mean and the population standard deviation. If I have the population mean and the population standard deviation, I can then start working on the sample mean problem. This information clearly is going to help me, because this says that the mean of a probability density function is equal to that, and the variance of a probability density function is equal to that. So I can use these two formulas to get me what I need from the population. Now, in a nutshell, the population mean is equal to the standard deviation between 0 and infinity of x times f of x with respect to x. Now, of course, our function is not x's, it's t's, so it's t f of t with respect to t. All right, now t f of t means t times f of t. So f of t is this thing right here. So I'll just replace that with that. So the mean is going to be equal to the integral of t times all of this with respect to t. Now, we can't sort of sub 0 to infinity into our calculator, but 60 seems like a good number. Actually, because it's just a straight up integral, we can probably use a larger number than that, but that's exactly what we're going to do. We're going to put this into our calculator and find the mean. One stepper. All right, so there it is, x times, and then all of this function here. Remember, x's not t's, because your calculator doesn't know what the t's are, and then we'll execute that. I really hope this doesn't take too long. All right, it doesn't take too long at all, and a very nice, neat answer, 15. The mean wait time for people to receive their fifth call is 15 minutes. That feels like I'm on the right track, because the question says determine the probability that the mean waiting time from the sample is more than 16 minutes. You would expect the population mean to be close to like this, let's see how much the sample mean is. So 15, I feel good about that. Now, of course, we've got to pull the same stunt for our variance, and then we'll go find our standard deviation from that. So variance. So I've taken this variance formula and I've put it down here. Instead of x's, I've put t's. Now you can see I've kept mu in there, but I know what mu is because I just calculated it. It's 15. So let's put 15 in there. And of course, we put this into our calculator and we solve. Now, because these are actually quite similar to each other, just a small edit. Changed x to x minus 15 squared. We'll execute that. Quick think, and we get 45. Variance of 45. Now, of course, we should know that variance, the standard deviation is the square root of variance. So straight away, we know what the standard deviation is. So what do I have now? I have the population mean and the population standard deviation. So from here, this question is super simple, because if I just said to you, hey, the population's mean is 15, the population standard deviation is root 45, determine the probability that the mean waiting time from this sample is more than 16 minutes, super easy. Now, interestingly, the QCAA did want something specific for you to receive a mark here, and they wanted you to do the following at this stage. They wanted some acknowledgement that because the sample was large enough, sufficiently large is what they've said, the distribution of the sample mean is normally distributed. And that's because the random sample is 80 workers. Generally, if it's greater than 30, we consider that the sample means will be normally distributed. All right, so from here, we can find the standard deviation of the sample means. So the population mean was 15, so the sample mean will also be 15. The standard deviation of the population is root 45, so the standard deviation of the sample mean will be root 45 over root 80, because 80 is the sample size, and that's a very neat number. It's 0.75. So I can now draw a normal distribution of the sample mean distribution. Boop. Mean of 15, a standard deviation of 0.75, and the question is asking us, determine the probability that the mean waiting time from this sample is more than 16 minutes. Boop, 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 boop. I'm trying to calculate this area right here. So, one more trip to our calculator, and this question is done. All right, so we are going distributions, normal distributions, NCD, and we are saying that the lower is 16, the upper is a very, very large number, the standard deviation is 0.75, the mean is 15, and we'll draw it to make sure that we don't make any mistakes. Looks about right. The probability that someone will wait more than 16 minutes before they reach their 5th phone call is 0.0912. Done. All right, like I said, a pretty intimidating question, but if you think about what the question's asking you to determine and then realize that you've got some sort of population at play here, not too bad at all. All right, celebrate. And that is it. That is the end. That is the final question. I have now made all 152 questions from the QCAA. Every video is out there. You can go and check them out. If you've been playing along for the whole 30 weeks, congratulations, you've done it. You're probably ahead of 99% of students who didn't do this stuff, and you've still got a couple of weeks to go before your exam. Plenty of time to jump back in, refresh your memory, do some more questions, find some other practice papers, but fantastic. Good job. I'm proud of you. Good luck.